All right, hello and welcome. Excuse me. We are continuing our discussion of electron configurations in chapter 3. On Tuesday, we were able to cover everything through the noble gas abbreviation. And tonight we're going to finish that discussion, give you everything you need to know for this course about electron configurations. If you take general chemistry, Chem 200, you'll pick up a few more details that isn't taught in this course. But tonight we will conclude our discussion of electron configurations and then dive into chapter 4. All right, so where are we at? So let's pull up our periodic table. So we now know how to use the noble gas abbreviation. So for example, let's write the electron configuration for argon. All right, now argon is right here. Its nearest noble gas with fewer electrons is neon. So argon's electron configuration starts with neon in a bracket because it has all the electrons of neon plus some additional. Now, if you look at the period that argon's on, it's on the third period. Now we start, to count our way over, we start on the very edge of the periodic table, count 1, 2, so we're 2 spaces in to the S block. All right, but now we're about to jump over from the S block to the P block. So we're still on the third period, but we filled our S subshell. Now we're about to fill P. And to get to argon, we have to move 1, 2, 3, 4, 5, 6 spaces in. Sorry, hang on. I wrote this in the wrong layer. 6 spaces into the P block, right? 1, 2, 3, 4, 5, and 6. So the electron configuration for argon is neon in a bracket, 3s2, 3p6. Let's take a look at the electron configuration for calcium. I know we ended with this one, but we're going to do it again by way of review. So calcium is here. Its nearest noble gas is argon. So we're going to begin writing calcium's electron configuration by putting argon in a bracket because it has all the electrons of argon plus a few extras. Now calcium is down on the 4th period, so we throw a 4 right in here. Calcium is in the S block, and so we start on the very edge and move 1, 2 spaces in. So this will be 4s2. Now, I want to remind us of something. There's something very subtle happened. that you may not have noticed, which is also totally fine, and that's why I'm pointing this out. Remember when we wrote out the different shells? On the first shell, there's one s orbital. On the second shell, there's one s and 3 p orbitals. On the third shell, there's one s orbital, 3 p orbitals, and 5 d orbitals. And then the fourth shell has it all. 1s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals. So notice something. We said that calcium has all the electrons of argon plus 2 in its 4s subshell. What about, the d orbitals? Calcium started filling the 1s subshell on the fourth energy level without putting any electrons into the 5d orbitals on the third shell. Because remember, the first principle for electron configurations is you have to fill the lowest energy shells first, and calcium went from, with argon, we've put electrons in the 3s and the 3p subshells, but then calcium started filling the 4s subshell before it put any electrons in the 3d subshell. Why is that the case? Well, it turns out that the energy levels for the 4s subshell and the 3d subshell are very, very, very close. All right? They're very, very, very close. Energy of the 4s and 3d subshells are close. They're close, but it turns out that the 4s subshell is lower in energy, slightly lower in energy than the 3d, and that's why the 4s fills first on calcium before the 3d fills. Before you put any electrons in the 3d subshell, you first fill the 4s subshell. Now you may be going, oh no, this is terrible, this sucks, because now here's this weird detail that I got to remember. Let me point something out to you. You actually solved this problem correctly last lecture, right? We wrote the electron configuration for calcium correctly without knowing this rule. The beauty of using the noble gas abbreviation and the periodic table is it takes care of this for you. You automatically filled the 4s subshell before you started putting electrons in the 3d subshell. All right, so this is another reason why I advocate using the noble gas abbreviation and the periodic table, is it handles that for you. You didn't even know this was the case, that the 4s subshell was lower in energy than the 3d subshell, and you wrote the correct electron configuration anyway. All right, the one time where you'll have to keep track of this, the one thing you've got to keep track of is when you enter the D block. Let's write the electron configuration for scandium, which is right here. You'll notice it's one space past calcium on the periodic table. All right. So scandium has its when you look at scandium, its nearest noble gas with fewer electrons is argon. So we throw argon in a bracket. All right. Hang on. I keep messing up my layers here. There we go. Throw argon in a bracket. Now we look at the period scandium's on. And scandium is down on the 4th period. So 4, and we're filling the S block. Now here's the moment of truth. The one thing you have to always keep in mind is the division between the S block and the D block. All right. You'll notice if we count over with our electrons, we go 1, 2 spaces in, right? So this is 4s2. The thing you have to remember about crossing from the S block into the D block is your energy level shifts. If you're at 4s, when you move into the D block, it is 1 level lower because remember, the 4s filled before the 3D, and so when you go from the S block into the D block, your energy level shifts down by 1. So this will be 3D1, because we moved 1 space into the D block. All right, and this is true every time for every electron configuration. All right, every electron configuration will have this situation in it. The shell of the S block is always 1 higher than the D block shell. Let's see. Yes. That is correct. All right. So that's the thing you got to keep in mind. When you're crossing from the S block into the D block, you always drop your energy level by 1. All right, so let's do a few more examples. Let's write out so with these, let's write the electron configuration and orbital diagram for each of the following. Let's go ahead and do iron. All right, so first we have to find iron on the periodic table, and it's here in the D block, so that should pop a red flag. You find your nearest noble gas with fewer electrons, which is argon. Excuse me. Argon's your nearest noble gas with fewer electrons. Next, we find the period that iron's on, and it is down on the 1, 2, 3, 4th period. So we're starting with the 4th period. We're starting in the S block. We're going to count 1, 2 spaces in. So this is 4s2. And then as we cross over, we are going to drop our energy level down by 1 because the D subshell will always have will always be 1 shell lower, 1 energy level lower than the S subshell you just filled. So we cross over and we count over to iron. 1, 2, 3, 4, 5, 6. So the electron configuration for iron is 4s2, 3d6. Now let's draw the orbital diagram. And again, remember with the orbital diagram, we are just looking at our valence electrons. So we have the 4s subshell, and then we have the 5 orbitals of the 3d subshell. Yes! Blake, great question, sorry. We'll see what happens with the D subshell in our next example. So stay tuned. First, let's write the orbital diagram here. So we have 2 electrons in our S subshell. So we put 2 electrons in our S subshell. And now we have 6 d electrons. Now remember, electrons repel each other. They don't want to share an orbital if they don't have to. And we have 5 d orbitals here. So we're going to put 1 electron in each one. And then, so that's 1, 2, 3, 4, 5. And then we have to put a 6th somewhere. Doesn't matter where. So that is the orbital diagram and electron configuration for iron. All right, let's see what happens. Because so we fill the 4s subshell first because it is lower in energy than the 3d subshell. So whenever you're filling the d orbitals, the energy level will always be 1 below the energy level of the s orbital you just filled. All right, let's do GE, germanium. All right, germanium is right here. Oops, let me colorize this. There we go. Its nearest noble gas with fewer electrons is argon, so we're going to throw that in a bracket. Next, we have to establish the period, and germanium is down on the 4th period. So we're on the 4th period, and you'll notice germanium is all the way over in the P block. Now we've done elements in the P block before, but we've never done a P block element after crossing the D block. All right, so this will be a bit of a new experience. Let's figure this out one step at a time. First, we're going to fill our S subshell, and And we do so starting on the very end, counting over 1, 2 spaces. So this is 4s2. Now we know, so if we're dealing with 4s, we know that when you move into the D block, you have to drop your energy level by 1. So we're going to fill our 3D subshell next. So we count over 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 10 spaces into the D block. We come to the very edge of the D block. And now you'll notice we're about to cross over into the P block. We have to get to germanium. What happens to the energy level there? Well, we've already filled our 3D subshell, yes, but we've already filled our 3p subshell, right? When we did the electron configuration for argon, that has a full 3p subshell. So when we cross from the D block back over to the P block, we are shifting our energy level back up. The thing to remember is that your S block and your P block will always have the same energy level. They will always be on the same shell. So if you're dealing with 4s, by the time you make it to P, it'll be 4p. If you're dealing with 3s, 3p. 5s, 5p. They will always be the same. D is the only one that shifts down. D is the only one that's funky. Everything else makes sense and is the same. All right, so now let's count over to germanium. We've got 1, 2 spaces. So this will be 4p2. That is our electron configuration for germanium. 4s2, 3d10, 4p2. Let's write the orbital diagram. We have the 1 orbital in the 4s subshell, the 5 orbitals in the 3d subshell, and the 3 orbitals in the 4p subshell. There are 2 electrons in the 4s block for this molecule, atom. There are 10 in the D subshell. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then there are 2 electrons, 1, 2, in the 4p subshell. So this is the electron configuration and orbital diagram for germanium. All right, we're going to do a couple more examples just to get some good reps in. So let's do something fun like palladium. That stuff that was killing Iron Man in Iron Man 2. Palladium is right here. We have to look to its nearest noble gas with fewer electrons, which is Krypton. Superman's home planet. Wow. We've got an Iron Man killer and Superman's home planet all in one example. That was not planned. So now we need to figure out the period that we're on. For palladium. And palladium is down on the 1, 2, 3, 4, 5th period. So we're starting with 5s. And then we've got to keep in mind, we know we're going to land in the D block, and D is always shifted down by 1. So we're dealing with 5s, 4d. So let's count our way over. We count 2 spaces into the S block. So we've got 2 electrons in the 5s subshell. And then for D, we go 1, 2, 3, 4, 5, 6, 7, 8 spaces in. So 5s2, 4d, 8. Our electron configuration, sorry, that is our electron configuration. To write out our orbital diagram, we have to write the 1 orbital in the 5s subshell and the 5 orbitals in the 4d subshell. And we have 2 electrons in the 5s subshell, and then we have 8. So 1, 2, 3, 4, 5, 6, 7, and 8. All right, let's see. There's a couple questions up in here. Let's see. For the test, do we have both diagram and configurations for our answers? Rock, so the first answer to your question is both orbital diagrams and electron configurations are a fair game for the exam. I haven't written it yet. I've started writing it, but I haven't gotten to the electron configuration portion. So I don't know how exactly they'll manifest, but both of these are totally fair game. Let's see. Okay, Brianna, how do you know how many lines to put for the orbital diagrams? Okay, great question. So, Brianna, these, and there's actually a reason why I color-coded them. Let me pick something that's a little off. Pick this weird brown. These come straight from here. So you look at the number of electrons in the electron configuration, and that's how many electrons, because that's what those lines are. In the orbital diagram, those are electrons. The number of electrons in the electron configuration will equal the number of electrons in the orbital diagram. Same here. These 8 electrons in the electron configuration are these 8 electrons in the orbital diagram. So however many you get in the electron configuration, those are the number of electrons you have to house in, in their respective subshells in the orbital diagram. The arrows are determined by the number of electrons in the lines. Oh, sorry. Okay. Now I understand your question. Brianna, that is a great question. Here's the thing to remember. Remember that that little diagram that I wrote on each shell. Well, so actually I don't have to write out the whole thing. So in each shell, actually, I'm going to start this slightly differently. And I'm actually going to clear the screen. So, Brianna, the shell number tells you the number of subshells available. All right, so on the first shell, this tells you, so we've got n equals 1, n equals 2, n equals 3, n equals 4. This tells you there's one subshell. Which is S. On the second shell, that number 2 tells you that you have 2 subshells. S and P. The third shell has 3 subshells available, which are S, P, and D. And then the fourth shell has 4 subshells. S, P, D, and F, which we're not going to talk about the F subshell in this class. If you take Gen Chem, you'll talk about it there, but we're not going to deal with the F subshell. All right, so each shell tells you, that number tells you how many subshells are available. All right, now, when you talk about every S subshell, every S subshell has 1 orbital. There's always 1 orbital in the S subshell. For the P subshell, every P subshell, everywhere it exists, will always have 3 orbitals. Doesn't matter if it's on the 2nd level, 4th level, 5th level, there's always 3 orbitals in the in every P subshell. Every D subshell has 5 orbitals. All right, and again, I'm not gonna test you on the F subshell. You're not gonna do any examples or problems with the F subshell, but just for the sake of completeness, I'm sure you can see the trend: 1 orbital, 3 orbital, 5 orbitals. The next one's also going to increase by 2. There are 7 orbitals on the F subshell. So it doesn't matter which energy level you're dealing with. It doesn't matter what shell they're on. The S subshell will always have 1 orbital. P will always have 3. D will always have 5. F will always have 7. And these numbers, these orbital numbers, these are the lines in the orbital diagram. So for example, if we blip backwards, a little further backwards. Not that one. Now let me grab the periodic table. So if you look at our previous example, you'll notice that we're dealing with an S subshell, so there's 1. When we deal with a 4D subshell, there are 1, 2, 3, 4, 5. Each line is an orbital. Brianna, you are so welcome. Okay. Whoa. That just got way more chaotic than it needed to be. Okay. That is correct. Each orbital can hold 2 electrons maximum. That is totally correct. All right, let's do one more example. Let's write the electron configuration for, oh, nope, new slide, for iodine. All right, now if we look, iodine is number 53. Its nearest noble gas is krypton. So we throw krypton in the bracket because iodine has all the electrons of krypton plus some extras. All right, next we look at the period that iodine falls on. It's on the 5th period. We're going to start, and again, you'll notice we've got the S and the P blocks both in play, but we've got to travel through the D block. We start on the 5th period, so we know that iodine will have 5s electrons, but then we cross from the S to the D. We've got to drop our D down by 4, but remember, when we get back over to the P block, the energy level, the shell for the S and P subshells will always be the same. All right, so let's begin our journey through. First, we start on the very edge, count 1, 2 spaces into the S block. So this is 5s2. Now we're about to cross into the D block, so we write 4d, and we cross 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All 10 spaces through the D block. When we come out the other side, we're shifting back up because our P energy level and our S energy level are always the same. And then we go 1, 2, 3, 4, 5 spaces in to the P block to get to iodine. So this is our electron configuration. Now let's write our orbital diagram. We have 1 orbital in our 5s subshell. We have 5 orbitals in our 4d subshell. And then we have 3 orbitals in our 5p subshell. Now we look to the electrons in our electron configuration to properly fill our orbitals in our orbital diagram. So the 5s subshell has 2 electrons. The 4d subshell is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the 5p subshell has 1, 2, 3, 4, 5. 5 electrons in the 5p subshell. All right. At this moment in time, you actually can handle any electron configuration that / orbital diagram that would show up on the exam. You've seen it all. I will not test you on the F block. So if you're wondering, okay, so what does that mean specifically? I will spell it out explicitly for you. I will ask you the electron configuration for any element that I'm boxing in here. hydrogen to lanthanum. Could be on the exam. All right, I won't go beyond lanthanum because I haven't taught you how. So if you're practicing on your own, you're looking to push the edge of the envelope, don't stray past lanthanum. There's literally no point for this class. But anything between hydrogen and lanthanum, 100% fair game. All right. We are almost finished with chapter 3. The last thing we have to talk about in chapter 3 are periodic trends. And the first is a trend known as atomic radius. Great question. Daisy, helium is a noble gas, but fluorine is not. Fluorine's not a noble gas. All right. Now, atomic radius. Oops. Another way to think about atomic radius is you could consider this atomic size, because atoms are more or less spherical in shape, and so the radius of a sphere will tell you how big the sphere is. The radius of an atom will tell you how large the atom is. Now, so you could consider this, i.e., this tells you the size. All right. Now, the definition for atomic radius is the distance from the nucleus to the valence electrons, which are the electrons in the highest energy shell. All right, so that is the definition for the atomic radius. There we go. So the way to like kind of envision it is you have, you know, your proton, you have your electron in orbit, and the atomic radius is that distance, because you may have electrons that are in a smaller orbit, right, on a lower shell. But the atomic radius is the distance from the nucleus to the farthest flung electron, right? So that's how it shows you how big the atom is. And there is a predictable trend for atomic radius or atomic size that the periodic table follows. So as you move from the top of the periodic table to the bottom, the atomic radius increases. So the closer you are to the top, the smaller the atom is. The closer you are to the bottom, the larger the atom is. So if I were to ask you, which is larger? And I give you two atoms, let's say nickel versus mercury. All right. What you have to do is find these two elements on the periodic table and determine which one is lower down, because the one that's on the lower period, the one that has the higher energy shell, has electrons furthest from the nucleus. It's going to be larger. So nickel is located here. Mercury is located here. Mercury is larger because it's lower down. What about, let's do another example. Let's compare fluorine versus strontium. Well, fluorine is located right here. Strontium is located right here. You're like, those are really far away from each other. They are, but to find the size, fluorine is on the second period. Strontium is down here on the fifth period, which makes strontium larger. All right, so that's the biggest differentiation between atomic radii. When you're looking for a larger atom, pick the one that's lowest down on the periodic table. When you're looking for a smaller atom, pick one that's higher up. All right, where things get a little dicey is what happens when, so same question. Oops. What happens if I give you two atoms to compare that are on the same period? What if I ask you, which is larger? Carbon or fluorine? Both of these atoms are on the second period. All right? Second period. So how do you determine which is larger and which is smaller? Right? There is a trend. So you always look for which one's lower, that one's bigger. If they're on the same period, we need a tiebreaker. And there is a different trend as you move from the right of the periodic table to the left. All right. What I want to do is compare carbon to fluorine. If we look at the electron configuration for carbon, its nearest noble gas is helium, and it will have an electron configuration of 2s2, 2p2. If you look at fluorine, same noble gas abbreviation, 2s2, or sorry, same helium core, but it'll be 2s2, 2p5. You have to count your way 5 spaces over into the p block. All right. You'll notice for carbon and hydrogen, that the valence electrons, the electrons that are furthest from the nucleus, the valence electrons are in the same shell. Right? We know this. That's why we have a tie on our hands. They're in the same shell. So theoretically, they're the same distance from the nucleus, but there's a subtle difference. All right, and this is where the tiebreaker comes into play. We have electrons that are roughly the same distance from the nucleus, but there's one critical difference between carbon and fluorine. Carbon has 6 protons. Fluorine has 9 protons. And we know protons are positive and electrons are attracted to them. Because fluorine has more protons. Its electrons feel a greater attraction to its nucleus than carbons do. All right, the electrons, because there's 9 protons in the nucleus of fluorine, the electrons of fluorine feel a greater attraction and they squeeze in just a little tighter than carbons do because there's more positive charge. There's greater attraction. They squeeze in a little bit more, and this makes fluorine slightly smaller than carbon. It's greater proton count. Its greater proton count means that it is slightly smaller. Than carbon. So if you have a tie, you have 2 things on the same period, the tie-breaking trend that you need to remember is as you move from the left of the periodic table to the right, your size decreases. So the further to the right you are, the bigger you are. If you're on the same period only, the further to the left you are, the larger you are. The further to the right you are, the smaller you are. So since carbon is further to the left, that means that carbon is the larger of these 2 elements. All right, let's see. Yes, correct. Correct. This only applies if they're on the same period. All right, so let's do some examples now that you can handle any 2 elements on the periodic table. You know everything there is to know about atomic radius. All right. So we're going to play which is bigger. Which is bigger game. And let's begin with zinc versus tellurium. All right. Zinc versus tellurium. Sounds like a weird sci-fi lawsuit. All right, so in the case of zinc versus tellurium, we need to locate these guys on the periodic table. Zinc is right here. Tellurium's right here. Now, the first thing you got to do is look at the period they're on. If they are not on the same period, and these are not, you always roll with the lower of the two, right? So because tellurium is on a lower period, tellurium is larger than zinc. Yeah, Daisy, spot on. All right, let's do another one. Let's do rhodium versus xenon. First job is we got to locate them, right? We may not know where all of these things are. Rhodium is right here, number 45. Xenon is right here, number 54. Because these two are on the same period, right? They're both on the 5th period. We have to go with the tiebreaker, which is the further to the right you are, the smaller you are. So rhodium wins the tie between which one is larger, which one is smaller, only because they're on the same period. All right, let's do one more just for good measure. Let's take a look at let's do bromine versus sulfur. Bromine is right here. Sulfur is right here. And because they're not on the same period, we are only looking at which one's lower. And that's going to be bromine. So bromine is larger. That is only your tiebreaker. Rox, you only want to look at the proton count in the event of a tie, in the event that they're both on the same period, because in this case, bromine has more electrons than sulfur. But in the previous case, if you look at xenon and rhodium, xenon has more electrons, but it's smaller. So the proton count doesn't reliably trend with which one's bigger or which one's smaller. It changes. You use your proton count only if you've got two things on the same period, and if you do, the one with the higher proton count is smaller. But that's only when they're on the same period. Yes. Rox, exactly. When you're looking at rhodium versus xenon, number of protons is how you determine them because they're on the same period. There will be a decent amount of atomic radius on the exam. It won't be exclusively atomic radius. There are going to be sig figs and other nasty things too, but at least you get this. This is not too shabby. All right. So atomic radius, this brings to conclusion our discussion of atomic radius. We only have one final topic to discuss in this chapter, and that is something called electronegativity. Which I will abbreviate as EN from here on out, mostly because it's such a long word to have to write over and over. All right. Electronegativity. So, okay, good. So what is electronegativity? electronegativity is a measure of how bad an atom wants more electrons. All right, electronegativity is a measure of how badly an atom wants more electrons. And the more it desires electrons, the greater its electronegativity. All right. That is the definition of electronegativity. This is actually a measured quantity. There are numbers associated with this that we'll actually get to a little bit later this semester. So let's look at the trend. The periodic trend. So electronegativity trends with the periodic table, and it increases. Oh, hang on, there we go. As you move from, as you move from the bottom of the periodic table to the top, electronegativity increases. And as you move from the left to the right, electronegativity also increases. All right. So the most electronegative are going to be right up in here on the top right. The least electronegative are going to be on the bottom left. All right. So let's put this into practice. Now, the rules for electronegativity are it's a little less cut and dry than atomic radius. All right, so let's do some examples. Which element is more electronegative? It kinda is. It increases as you move from right to left. Yeah, Rox, that's very, very astute. All right, so let's apply our rules. Which is more electronegative? Let's start with fluorine versus carbon. If we look, you can see that fluorine is here, carbon is here. We know that electronegativity increases as you move to the right of the periodic table. So fluorine is more electronegative than carbon. All right, that example is pretty cut and dry. What about oxygen versus tellurium? And again, looking at the periodic table, oxygen is here, tellurium is here. When you look at the trend going vertically, the higher you are on the periodic table, the more electronegative you are. So oxygen is more electronegative than tellurium. Again, another cut and dry example. Where things get dicey is when they're placed differently. So, for example, if I ask you, what is more electronegative? Phosphorus or bromine? Phosphorus is here, bromine is here. You'll notice that phosphorus is 1 higher, but bromine is 2 further to the right. So we've got phosphorus 1 higher, bromine's 2 further to the right. Because bromine is 2 spaces over to the right, but phosphorus is only 1 higher, bromine is more electronegative. It's 2 spaces over as opposed to phosphorus's 1. Let's do another example. Let's do oxygen versus bromine. You'll notice that in oxygen versus bromine, oxygen's here, bromine's here. In this example, bromine is 1 further to the right than oxygen, but oxygen is 2 spaces higher than bromine. So in this case, oxygen is more electronegative because it's got a 2 space advantage to bromine's 1, right? So oxygen's going to win. Now, what happens when we really go for the jugular? This is the hardest electronegativity question I can ask you on an exam, and I'm going to ask you right here in lecture. Oxygen versus chlorine. Actually, all this orange is confusing. I'm going to pick a different color. Oxygen versus chlorine. Chlorine is 1 space further to the right, but oxygen is 1 space higher. Who's going to win? This is the true tie, right? There isn't any like, oh, this one's 2 spaces further. No, it's 1 space further, 1 space further. What wins? Further to the right or closer to the top? The answer is closer to the top wins the tie. Oxygen is more electronegative than chlorine. So if you've got 1 versus 1, pick the one that's higher. But if you've got one that's 1 higher but one that's 2 spaces over, pick the one that's a greater number of spaces over, all right? In the case of a tie, you pick the highest one, but only if it's tied. All right. There we go. Yep. Daisy, you got it. Okay. So that is atomic radius. That's electronegativity. And that brings to a close our discussion of chapter 3. All right, and this brings us to chapter 4, which will go on for quite some time. All right. So chapter 4 is all about one thing. Chapter 4 is about bonding. All right, it's all about bonding. And bonding comes in 2 flavors. There are 2 types of bonds that we're going to look at in this course. The first is ionic. The second is called covalent. All right, so we have ionic bonds and covalent bonds. we're going to begin our discussion with ionic bonds. So we're going to talk about ionic bonds for a while, then transition to covalent. All right. So let's talk about ions. So if we're going to talk about ionic bonding, we need to know what ions are. All right. Now, ions are, or an ion is an atom or group of atoms. We'll get to those in a bit. An atom or group of atoms that have a net charge. All right, what is a net charge? A net charge is an imbalance or, in other words, different quantities. Different quantities or an imbalance of protons and electrons. All right. For example, if you have the atom sodium, and you look it up on the periodic table, sodium's number 11. Sodium has 11 protons and 11 electrons, because elements have the same number of protons and electrons. What would happen if sodium lost one electron? If sodium lost an electron, it'd still have 11 protons. But if it had 10 electrons, now there's an imbalance in positive and negative charges. And because there's one more proton than there are electrons, sodium would have a positive charge. This would be an ion. An ion with a positive charge. Let's look at another example. Let's look at fluorine. All right. Fluorine, the element, the atom, has 9 protons and 9 electrons. All right. What would happen if fluorine gained an electron? Well, if fluorine gained an electron, its proton count would not change. It'd still have 9 protons, but it would have 11 electrons. No, it wouldn't. That's if it gained 2. If it gained 1 electron, it would have 10. I promise I can do math. Because fluorine has now 1 more electron than proton, it's got 9 positive charges, 10 negative charges. It has a total charge, or a net charge, of -1. All right? So this is sodium as an ion. This is fluoride as an ion. Because sodium is a positive ion, positive ions have names. They're called cations. Fluoride is a negative ion. Negative ions have names. They're called anions. All right, so there are 2 different types of ions. Ions are just any atom or group of atoms that have an imbalance in electrons and protons, a net charge. If the ion is positive, it is called a cation. If it is negative, it is called an anion. All right? Okay. let's see. I'm looking at what comes next. You know, I think I'm going to pause here. This seems like a good place to stop. The place that we're about to dive in is kind of, it's a little bit on the lengthy side. So we'll put a pin in lecture here. We'll resume on Tuesday with a discussion of, now that we know what cations and anions are, where do they come from? How are they formed? So that's what we'll get to in lecture on Tuesday. All right, so that does it for us. I will catch half of you, section 62, in lab at 6:45, and I will catch the